Welcome. Thank you all for joining us in this inaugural session of Shadow the Scientist for the CBSE community of teachers and students. My name is Jamika Marshall, and I'm pleased to serve as the Shadow the Scientist coordinator. For this special session, we have the Shadow the Scientist founder, Raja Guharthakatha, to say a few words to get us started. Raja.
Thank you, Jamika. Thank you very much. My name is Raja Guharthakatha. I've been a professor of astronomy and astrophysics at the University of California, Santa Cruz, for coming up on 30 years. I'd like to add my hearty welcome to the students and teachers from the CBSE schools who are on this Shadow the Scientist call and live stream, and to the dignitaries on the call. This is a special moment for me because I was a school student in Kolkata many years ago. My school was in the ICSE and ISC board, not the CBSE board, but it's only a matter of time before we also invite students from other boards to take part in events like this. Many thanks to Dr. Emmanuel and Mr. Hilal from CBSE, to Mr. Sanjay Kumar for initiating this entire collaboration, to my colleagues, Jamika Marshall and Professor Arvind Rao, who met with Dr. Emmanuel and his colleagues, and to my friend and former student, Dr. Brian Lamont, and the Gemini North team for making this session a reality. Now over to Dr. Emmanuel, who would like to say a few words.
Actually, I believe Dr. Emmanuel lost his connection, and because we are heavily full in our session, I'm unable to readmit him. So we will move to the remarks by Mr. Sanjay Kumar. Mr. Kumar. Mr. Kumar, if you are able to message me, please send me a direct message so that I can we can make space for you to share your remarks at any time during the session. Okay, so it's 20 minutes past the hour. So what we'll go ahead and do is move on to beginning the session. We have the privilege of shadowing the observing team here at the International Gemini Observatory North. Observations are currently underway right here behind me in the remote control room. Now, our guide for this session, we have several. It's going to be Brian Lameau, Zach Hartman, and Charlie Figueroa. I'm sorry. Oh, yes. And Emily Peavy, as well as Ekta Shah. Here we are. I do see Mr. Kumar's video is now enabled. So we will pause there and go back to Mr. Sanjay Kumar. Welcome, Mr. Kumar and distinguished guests.
It's a pleasure to join with you. Can you hear me?
We can, sir.
Yes, sir.
So it's a pleasure to hear you. And last time I spoke to Professor, whom I can see on the screen, you were on the way to US at Indira Gandhi International Airport.
That's right.
And this has been a culmination of long-standing collective effort. And I'm so glad that you have chosen to connect with 1,000 schools of ours, some of the best schools in India, which are affiliated to Central Board of Secondary Education. And I think this is a wonderful chance for any child to be able to sit in the school and to get connected to the stars through some of the best telescopes operating all over the world. So I would not want to take too much time. Thank you, Professor. Thank you for facilitating it. And I hope that this is a continuing process, and in due course of time, more and more schools and more children in our schools get to see what you've been seeing and the excitement you feel when you look at the sky and what the stars tell us. So I think this is a great opportunity to arouse the interest of students towards astronomy, and also what a wonderful new world awaits them. Thank you, Professor.
Thank you, sir. Thank you, Jamika. Thank you, Ekta, Brian. Thank you very much, sir. I remember that Zoom call we had. Actually, it was a WhatsApp call when I was on my way to the airport. It was in December, but so much has happened in the last 4 months. So much work has gone on. Jamika spearheaded this. I'm so happy that this is happening. Thank you, sir, for inaugurating this session.
Thank you. And I welcome all the children who have joined us from the 1,000 schools in India, their teachers, and this is a great opportunity. We never as a child had this opportunity.
Thank you so much for those words of welcome, Mr. Sanjay Kumar, and welcome to all the distinguished guests who I see there in the room with you. As we continue with this session, post your comments and questions in the chat, and the observing team will answer them as soon as they can. So with that being said, we are going to head inside of the control room. On the screen, you can see HBF control room. That is actually the room right behind me, and we will hand off this session to Zachary Hartman and Charlie Figura. Hello, everyone in the HBF control room.
Hey, Jamika, how's it going out there?
Oh, it's pretty good, Zach.
So yeah, we are currently in the middle of our observing night here. We've been on Sky for 2 hours? Hour and a half?
Yeah,
And so
science for a full hour.
yeah. So we have tuned the telescope. The telescope is now at its optimal operating right now. And we've been observing some exoplanets, host stars, looking for exoplanets around them, and also some dwarf spheroidal galaxies, and getting some images on those. Now, unfortunately, I can't really share the screen right now with you all because these computers are not connected to the internet that I'm looking at. And so, as soon as they are all, as Jamika and Brian and Emily are all set up in the room where they're going, they'll be able to share what we're seeing here. But so right now we just started a 5-ish minute observation on a exoplanet host star and trying to learn more information about that system. And that's pretty much what we're going to be doing for the next hour and a half before we go take some more images of dwarf spheroidal galaxies. And then we did have a special event happen today, which is a scientist somewhere in the world initiated what we call a rapid target of opportunity. And so what that means is we kind of drop everything and try and go take this target. And that's in the middle of the night. And I don't know how long to go for, but maybe you'll catch the beginnings of that. This particular target of opportunity is a supernova that just was detected. And so we're going to go and try and get a spectra and see all this information, all the spectral information, all these elemental abundance information for this particular supernova, and see what's going on with it. Let's hear. I mean, right now it is contrary to what our expectation was at the beginning of the night, it is a beautiful night on Mauna Kea. We have some clouds low on the horizon, but none in the sky really. And we have some great what we call seeing. So this is how seeing is basically a measure of how much the atmosphere interferes with our observations. And so right now the seeing is very low. In the case that we're looking at here, the value that I see right now is about 0.4. And I'm sure when Brian, Emily, and Jamika get back on, they'll dive more into what seeing actually means. But it is a very beautiful night, although even though the forecast said that it wasn't going to be that great, but it is turning out to be great. And yeah, so right now we're continuing to take this Maroon X observation. And so Maroon X in particular is what we call a high resolution spectrograph. And so what this means is it is capable of taking spectra, so basically taking light from a star and splitting it across wavelengths. It is capable. It is designed to get very high resolution on that spectra, so be able to pick out individual elements. And for these, and in particular for Maroon X, it's a resolution of 80,000, and so that means that we are able to go and discern individual lines very, very well. In particular, what Maroon X is really designed for is to get very good radial velocities. So for Maroon X, or for radial velocities, this is how fast a star is moving towards and away from us. And in particular for Maroon X, they want to detect the motion that a planet might affect a star. So as a planet is going around its host star, it is shifting the star a little bit around. And so with these measurements, we're able to see the change in the velocity of that star away from us over time. And so, yeah. So I am the observer tonight, but we also have an operator, Charlie. Do you want to explain anything about what we're doing tonight?
Sure. So I'm the operator. I am pretty much in charge of the telescope systems, the detector systems, basically making sure that everything up at the summit is operating correctly. I am in control of the telescope itself. So it's my responsibility to slew the telescope, to establish guiding, to make sure that we are looking at the correct target and have a good steady view. I'll respond to weather conditions. So as wind increases, we might close some of our vent gates or close up the shutter a little bit to keep the wind off the telescope, because wind will cause shake. And so Zach and I kind of work as a team. As the observer, Zach is in charge of controlling which observations we pursue. And when we do those, and then I set up on those, and he'll start those observations, start collecting the data that goes out to the researchers really around the world. As Zach mentioned, conditions tonight look really nice. We've got a little bit high wind, about 10, 11 meters per second on the summit right now. So most of our vent gates, our shutter are closed up a bit because that's a lot of wind loading on the telescope. But humidity looks really good. All the other conditions look really nice tonight so far. We're trying to get as much good observations as we can. The next few nights look to be pretty ragged in terms of cloud cover and humidity, all of which are bad for observation.
And so speaking of the next observation, can we go to Q1 2025, please?
Q1 2025, slowing. So there you heard Zach set us up, tell me which observation we need to go to. I started the telescope moving. Slew is the word that we use to describe telescope motion to a new target or to a new position. Watching the dome, watching the telescope move into position so that we can set up guiding and start that observation. We have 3 different instruments right now that we can swap between, and it's one of the strengths of our observatories. We have several instruments, depending on what kind of science we want to do, that we can move between on a minute or two's notice. So that if you want to do some imaging, take actual pictures, we can do that. If you want to do spectroscopy, look at the different wavelengths of light that are coming from a location, we can do that in very short order. And sometimes researchers will want to do both of those things. All right.
And as we're still working on some technical difficulties, if there's any questions, go ahead and type them in the chat. I know the chat's been moving really fast. We might not have been able to see questions that popped up beforehand.
Oh, that's annoying. What's going on?
Yeah, so when we target or when we slew to a target, when we're focused on that target, we have what is called guiding. And the noise that you just heard possibly is when guiding does not like to work, or we don't have enough counts to maintain guiding. And so we get a popping noise happening in the control room whenever that happens.
So what happened when we point to a spot in the sky, the telescope, the motors on the telescope are really good, but we generally won't be right on the target. And so what we use is a guide star, a nearby bright star that we will focus a specialized camera on. And that star is usually much brighter than the science target that we're looking for, but it's bright enough that we can use that star, watch that star, and if that star shifts slightly, we can move the telescope to compensate. The star isn't shifting, it's really the telescope that shifts, but that allows us to stay pointed in the exact correct spot. And that's what guiding is. We are actually looking at 2 different things at the same time. The science target and a guide star that enables us to keep looking precisely at that science target. All right, let's try closing the loops again. All right, Zach, we are guiding on P2 at 100 hertz.
All right, thank you.
So that means that our guider is looking at that bright guide star 100 times a second and making corrections 100 times a second to make sure that our position is precise. Now Zach's going to take over, since I've got the telescope in position, and set up the actual science observation from his station over there across the room.
Yep, and so we're doing a Maroon X observation. So I'm setting up the guiding that is actually within Maroon X. And so Maroon X is a fiber-fed instrument. So there's actually a fiber that we have to line up the star with and place the star on the fiber in order to get that light. And so I'm lining that up right now. And then when everything looks good, which it does right now, and I start the observation. And I have to make sure I go in and I check whether or what time the science needs and how many observations it needs. And for this one, it's actually a pretty long observation at 1800 seconds, but it only needs one. So I'm going to start that. And now we're here for 1800 seconds.
Hey,
Thank
Zach and Jamaica and Brian, I've pinned your control room on my Zoom call. I don't know if that means it's pinned for others, or do they have to each individually pin the control room?
We just have the video recording of the control room. We don't have video on any of their screens that they're operating.
Yeah, we're hopefully now that Jamaica and Brian are have rejoined, then maybe we can start sharing the screens. But for these computers in the control room, they are not connected to
Right,
the
right.
external internet. And so,
Right. No, I understand that. What I was asking, I guess, is I have pinned you guys, the Gemini control room. Does that mean it's full screen for everyone, or is it only for me?
Everybody see me waving?
I can see you waving. You're full screen for me. What I'm wondering is if that means it's full screen for others on their Zoom calls.
I think it is.
Okay.
Probably depends.
Oh, nope. It looks like no.
Yeah, a person says that pinning your screen would not pin it for others.
Yeah. Okay.
I'm not sure if there's a host that has pinned it, but we're able to see any presentation. Not able to see any presentation. Oh, okay, we just got spotlighted. Okay, and that looks like it. Okay, how is Maroon X used?
I guess I'm wondering in what sense. So I mean, Maroon X is a spectrograph. And so what this means is we take light in from an object and we split that light into its different and so for different stars, they'll have different features in that dispersed light in that spectra. And so using this, you can go and measure the depths of those features and determine abundances, like how much of a certain element is in a star. Or what you can do is you can see the shift in a star's lines, as from what I was describing earlier with the with radial velocities, where as the star is moving towards and away from you, these lines are blue shifted or red shifted. It's much like when you hear a siren coming towards you or away from you, you can hear it kind of increase, and then as it passes you, it kind of decreases away. It's a similar phenomenon to that for this radial velocity studies. And so in particular, Maroon X being this high resolution spectrograph, it's really, really sensitive to small radial velocity changes. And so in particular, it's designed to go find exoplanets around other stars. And it does that by basically when as a star rotates or goes around its host star, it changes the velocity that we see from it. So you see the shift in the star's normal velocity as this planet goes around. And with Maroon X, we're able to go in and detect what those shifts are and eventually get and use that information to better understand what the properties of that exoplanet are.
I had another question that's come in as well. What is a spectrograph? And a spectrograph is an instrument that essentially dissecting light. So the light that's coming into the telescope is getting broken up into all of its different wavelengths. And then if we know, as what Zach was describing with radial velocity is we look at the light, we look at how it normally behaves, and then we're seeing how that light is changing on the spectrum. So if it is shifted in one direction or another direction. So if it is shifted towards the blue, so if we have lines that are typically in one section and then it's shifted towards where we would expect to see more bluish light, that means that the object is moving closer to us. And then if it's red shifted, it's moving farther from us. So in detecting an exoplanet around a star, we're seeing how the gravity of that exoplanet is pulling and pushing on the star back and forth. And if that is pushing the star close to us or far away from us, and we're able to see that with our very sophisticated spectrograph, which is Maroon X.
And it vanished. Well, you could see what
There we go.
Okay,
Yes,
hello. Hello,
Hey.
hello. Can you hear us okay?
Yes.
Yeah.
Awesome. Okay.
Fantastic.
Okay, sorry about all that. We had tons of technical difficulties. There's a wonderful level of interest this evening, so we had to move things around a little bit. But I think we're all settled for the moment. So hi, I'm Brian. I'm here with Jamika. We've moved to a different part of our base facility here at Gemini North in Hilo, Hawaii. And right now I'm sharing, this is a real live screen of the Gemini North telescope. So I'm actually, so you all are shadowing us, and I'm actually shadowing Zach right now. So this screen that you're seeing right now is the Maroon X control screen, which is controlling the instrument, which is on the summit of Maunakea, which is not where we are. We're at the base facility in Hilo, Hawaii. So we're about 35 kilometers away from the telescope. And Charlie and Zach are operating the telescope. Zach is on the side of the instrument. So he is using this spectrograph, this Maroon X spectrograph. And this is the screen that he uses to control the observation. So I'm not sure how much you said about the instrument already, Zach, but I think I heard that there's somebody say spectrograph.
Sorry, Brian, we were just describing what a spectrograph is. Could you show on the screen like any feed that we're getting from the spectrograph?
Yeah, I would love to. So hold on one sec. Okay, so I'll just walk you through roughly what we see here. What we're seeing is the Maroon X screen. This is the star that the proposing teams wants to look at. So we have scientists from all over the world that ask for time on our telescope with our instruments. And we have a peer review process. So other scientists review the scientific merit of a proposal. And they say, yes, that's a good proposal. That's a good idea. No, that's not such a great idea. Why don't you come back another time and try again with a better idea? And so we choose from a pool of observations, the observations that we think have the most scientific merit given the conditions. And so as Charlie and Zach mentioned earlier, the conditions are wonderful tonight. That's good news for our principal investigator that is trying to look at a supernova later this evening, who is going to join us on the call in a second. And so we're going to be looking to do science that is very high leverage, that we think is kind of the best of the best science. So this is probably a fairly highly ranked proposal. I don't know what it is, but so we train on this star. We have a fiber. So basically the telescope collects the light. That light is then piped into this fiber. The fiber collects the light just from the star, a little bit of the sky, but mostly from the star. And then it pipes it to a dispersive unit, so like a prism, for example. And what we see here is the different orders, spectroscopic orders, coming from this star. So Zach is taking an actually probably from the previous star. So Zach is taking exposure right now. I think he mentioned that it's 1800 seconds, so 30 minutes. And once the 30-minute exposure is complete, then a readout will occur, and we will see the spectrum of the star here. This is the red portion of the detector. So this is basically red light. Yeah, as humans would see red, basically, and a little bit redder than that. And this is the blue portion. So we helpfully color code it so that we can tell which is which. And these little funny things here comes from what we call laser frequency comb. And it basically allows us precision to understand at a given location on our detector, what wavelength of light does that correspond to? And for these types of observations where you're attempting to measure, by and large, we're attempting to measure very small movements of a star, large on human scales, fast on human scales, but fairly slow in terms of cosmological velocities. we need to know very, very precisely the wavelength of light at any given location. So as the Doppler shift occurs due to the planet moving around the star and the star wobbling back and forth, we see tiny shifts in the wavelengths of light of different elements. And so we need to calibrate that very precisely, and then we can determine how much, or the proposing team can determine how much that star is moving, and can then infer a variety of different parameters about the stellar system, about the planets that are around it, and other properties of interest. So in some cases, we even measure the atmosphere of the planet by looking at a transit. These are typically very long observations. So basically, telescope's here. If you can see my video, telescope is here. Planet is orbiting around a star, and you see the planet go in front, and the elemental pattern changes. The planet then occults the star, and then the planet moves past the star, and you can take a kind of difference between when the planet is right in front and when the planet is completely separated from the star on the sky, and you can tell something about the chemical abundance of the atmosphere of the stars. So that's not what we're doing right now. I think we're probably just measuring a radial velocity. But as Zach showed right here, this is a wonderful example of, these dark bands that you see here. These are either atmospheric, so from our own atmosphere, from the atmosphere of the planet that's being observed, or from the atmosphere of the star that's being observed. And so the scientific team that gets these data then try to disentangle all these different signatures, remove the terrestrial aspect. Oops. I think our video just went away.
No, there you are. We're back.
Okay, we have a very
Brian and
finished-
Jamika, please let me know when it's okay to ask some questions.
Yeah. So I'll just say that in case that didn't come through, the scientists try to they receive these data, try to remove the terrestrial aspects of the data from the extraterrestrial, so the star and the planet. And so that's done through a variety of different calibrators that we take or they take. And yeah, please, Raja.
Mr. Sanjay Kumar has asked, what is HBF? It's Hilo Base Facility. Hilo is the name of the town where the control room is and where Brian and Jamika are. Ikta, you're not there, are you? You're in Davis, I assume?
Yeah, I'm in Davis.
So HBF is the Hilo Base Facility, base because it's at the base of the mountain, base of Maunakea. And that's what HBF stands for, Mr. Sanjay Kumar, HBF. Now, I did want to say, I got the sense that when I was in school, when I was the same age as many of the students who've joined, I had no idea what a spectrograph was either. So what I wrote, I'll repeat this because there's so many things in the chat that things are scrolling by. What I wrote is a spectrograph is something that takes the light of a star or other astronomical object and creates a very finely grained rainbow out of that. Very finely grained rainbow, so that you can see many distinct shades of violet, many distinct shades of indigo, many distinct shades of blue, etc. So you get thousands of colors instead of the 7 colors of the rainbow. You get thousands of shades. So multiple shades of violet, indigo, blue, green, yellow, orange, red. That's what a spectrograph is. And as all of the scientists have been describing, taking a spectrum of an astronomical object allows us to measure very important things about it, how fast it's moving and what chemical elements are present in the atmosphere of that object. And I know people asked about nebulae, and Ekta, you answered that. One of the things I was going to add to that is typically when you take a spectrum, whether it's with Maroon X or GMOS, one of the spectrographs, before you take a spectrum, you typically have already taken a digital image of the sky, and that way you know exactly which astronomical object you want to study with the spectrograph, you take the light of that object only and send it into the spectrograph. I
So
hope
Raja,
that's helpful. I'm sorry to interrupt here, but please take it away.
oh no, that was great. Thank you for the explanation. I just wanted to say that we have the distinct honor of having one of our principal investigators on this evening who actually asked us very kindly today, the observatory very kindly today, by pressing a button on his computer for us to take an observation of a supernova that he just discovered. And so he's not actually on the Zoom as everybody can see it, but he's on a different Zoom. So here he is on my computer. So this is David Jones, former UC Santa Cruz postdoc, and now a professor at the University of Hawaii in Hilo. I'm going to turn on David's sound. David, can you hear us okay?
Yep.
Perfect.
How's it going, everybody?
So David is going to tell us about the object that he discovered and what we're going to do with it later this evening. What Zach is going to do, Zach and Charlie are going to do later this evening. And I wonder, Zach, might you be able to bring up the OT with David's program, since I think he's comfortable sharing it? And maybe we could take a look at an image, at least from the OT. This is our Gemini observing tool. And if you could just tell me which screen that's on, that would be awesome.
3.
3, okay. So yeah, David, tell us all about your awesome supernova.
Awesome. Thanks, Brian. Yeah, really happy to be able to just find a supernova, trigger Gemini observations, sit at home, have them observed. Sometimes the telescope's really far away. For me, it's like a 10-minute drive. So this, I didn't discover the supernova. There are surveys that are just running all the time, taking new images of the sky, looking for differences with old images, happening relatively automatic, but then a person at some level has to pour through the data and see if there's anything new there. So, oh yeah, that's a really nice picture of the OT. So you can see there's this nice edge-on spiral galaxy. A supernova was discovered just off the center of it, and it seemed to be rising pretty fast. So
Hey, I think we're still pinned on
these,
the other Zoom.
sorry, let me know if anybody's trying to jump in there.
1 sec, David. Sorry, the connection here is kind of loose, so I think we just lost sharing for a second.
No worries.
Can everybody see? Zach, you guys can see?
Yep.
See.
Yeah, we can see the galaxy image and the supernova.
Wonderful. Okay.
I think that's a supernova. I'm
Yeah,
not sure.
so supernovae are exploding stars. This one is a type 1a supernova, which means it's comes from the explosion of what's called a white dwarf, which is what we think will happen to a star like our sun at the end of its life when it burns all of its fuel. And at the end, there will be a white dwarf in its core, which is just a really dense core of carbon and oxygen. And this will, I think it will have the mass of some large fraction of the sun, but it'll only be about the size of the Earth. So these things, they accumulate matter from some sort of companion star, and at a certain point, they gain too much and they explode. And specifically, we're really interested in how that explosion is happening for this program. So what we can do is we can look at the chemical elements that we see in the explosion, in particular, the carbon signatures, at very, very early times when you see the outermost layers of the explosion, and we're trying to figure out how much carbon is still there. Because if you see how much carbon is in the spectrum, that's a sign of how many of the elements were fused into other elements, which gives you an indication of how the explosion actually happened. Did it explode at the core? Did it accumulate some mass on the surface and explode there and then propagate into the core and then the whole thing blows up? So this is the program we've been carrying out this semester. I think this is the 3rd supernova we've triggered on. And we've gotten some really, really beautiful data. In particular, finding these things and getting observations within like the first 2 days after they explode is really, really difficult. And we think we've actually successfully done that for at least one of our targets, and the others we've gotten pretty soon after they exploded as well. For reference, these things are usually visible for maybe 2 months, and they're faint, and then they rise to some peak, and then they just slowly fade away over that month or two. But it usually takes them maybe 2 weeks to rise till peak, so you really have to be checking your data every night, seeing what surveys are discovering, and it really helps that Gemini has this program that basically I think will be on the sky maybe 6 hours after I put in the request.
So how young is this supernova, David? Maybe you said it already, but how long ago was this discovered?
Yeah, it's not like one of the youngest, but it's probably a week after it exploded.
And so why
So
is getting on it so early so important, and then following it up for, I guess you follow up for quite some time afterwards?
Yeah. Yeah, so usually how it works is you can, at the very earliest parts of the explosion, you can see the light from the outer layers, and then as it explodes, everything spreads out and it becomes kind of diffuse, and so you see into the inner part of the supernova. And so the older the supernova is, you see different layers further and further towards the core. So in this case, we're particularly interested in what's happening in these outermost layers, and to see that, you have to catch it young. And this is a really pretty new area in supernova science that we haven't been able to look at very much. For core collapse supernovae, you can actually see like the first part of the explosion as it passes through the outer layers of what used to be the star. For this type 1a supernova that we're looking at today, there's a theory that we're seeing interaction with a companion star that's actually pouring mass onto the white dwarf and causing it to explode. So there's lots of new physics, and each time you look in a way, you look at an astronomical object in a way that you haven't before, you're going to see something that you probably didn't expect to see. So that's why we're excited to just see the earliest observable part of these explosions.
And so I noticed that you're not using Maroon X for this, which was the instrument that we're currently taking observation. And you're not using GMOS, which is an optical instrument, which is similar to Maroon X in the sense that it absorbs optical light, but rather you're looking in the near infrared, so past the range of human vision. Why would you choose that to look at the particular supernova?
Yeah, a couple things. First is that Maroon X is this really beautiful high resolution spectrograph. When you see a supernova explode, there's a bunch of what we call ejecta. The supernova is moving towards you, part of it is moving away from you. What happens is that this introduces a Doppler shift. I guess you talked about radial velocities already. Here, when you look at a supernova, you're seeing lots of different velocities, and so it smears out these features, and you get these big, broad characteristics in the spectrum. So basically, there's no point in spreading out the light into these really finely spaced wavelengths, because you're not going to get any more information anyways. They just don't contain much information on scales like that. So I don't know if that was very comprehensible.
So the alpha velocities are in the neighborhood of like 1,000 kilometers per second or a couple thousand kilometers per second. Is that correct?
Yeah, more like 10,000.
10,000. Okay. And so
Yeah,
the resolution for Maroon X is roughly 1 meter per second. So that's a resolution almost 1 million times greater than what you need for your observation. And so with the higher resolution, you disperse out the light more, and so you can't get as much signal. And so you match your scientific need to your instrument. And so in the case of this instrument, GNears, the resolution is more like 100 kilometers per second or something like that. And so that's much better for your science, I guess.
Yeah. Yeah, and then we have the near infrared. So this is not visible light. It's a longer wavelength than that. What do I want to say about the infrared? I mean, basically the reason is that each element has certain chemical signatures, and the near infrared in particular can probe different temperatures. So you see, I think you see more ionized carbon lines in the optical and neutral carbon in the near infrared. I could be making this up actually, but you see different features in the near infrared wavelengths, different transitions of electrons and atoms. And so you can see different elements at different temperatures. And we have optical spectra of this object as well. And so this gives us complementary information so we can get as comprehensive a picture of the supernova as we can. You can also see through dust more easily, kind of like as the sun sets, it looks dimmer and it looks redder. So the same thing happens in astronomy as well. Objects look look fainter and they look redder. And when you look at redder and redder wavelengths, you're affected less by that dust along the line of sight between you and the supernova. So you can see through some more layers of the explosion in that way as well. It's one of the reasons we use near infrared supernovae for measuring distances too, which I guess I can get into if we want. But there are some advantages to an object being less obscured by dust between us and the object.
Thanks, David. We had a question in the chat about where the supernova is. And so actually the person asked where the supernova is in this picture. And I guess the static image, so this was an image taken at one particular time. And this was quite a bit of time before the supernova went off. And so I was wondering, you mentioned that at the very beginning that it wasn't you that discovered it, but rather observations from other telescopes and other analysis tools that allowed you to see this supernova and then to point our telescope at it. Might you be able to show a picture? I can hold basically my laptop up to the to the other camera. Yeah. Do you have a picture that kind of shows the like a differenced image or something like that that shows the supernova?
Yeah, let me share my screen and see if I can come up with anything here. This is from the Discovery Survey. This is the Atlas telescope, which is on Haleakala on Maui. Actually, I think there's one on Haleakala and one on Mauna Loa, the next mountain over from Maunakea. And this image doesn't look that great if you're used to looking at these beautiful pictures of the Hubble Space Telescope or JWST or something like that. But on the left-hand side, this is the image with the supernova in it. On the right-hand side, this is the image without the supernova. So you subtract one from the other because they look pretty much the same by eye. In fact, it looks like the object in the middle has more stuff in it than the one on the left, but it's actually because the one in the middle is lots and lots of images stacked together, so you can see deeper and deeper into the sky. But though you can't tell it with your eye, if you actually do that subtraction, then you see something like this image on the right-hand side, which is the supernova. So unfortunately, this isn't one of those like spectacular images of a supernova that you sometimes see in like HST images or something like that. Or if it was a giant like grand design spiral galaxy, you might see this beautiful supernova popping out along the edges. Here it's totally lost in the noise of the galaxy, and with this technique we can pull it out a little bit. This, I don't know how much you guys can see. This is kind of what the optical spectrum of the supernova looks like. So people search through the data and find these things and report them to what's called the transient name server, and they just get numbered alphabetically one after another. So this is supernova 2024 FXL. It was classified because people took the spectrum and looked at these broad features that indicate certain elements, primarily silicon here at 6,000 angstroms. There's, let's see, calcium here at 4,000 angstroms, and also at 8,000. So this kind of spans the visible range of wavelengths that your eyes can see and gets a little bit into the near infrared here at the end. But looking at those atomic features, you can see what kind of supernova this is. Then the other thing interesting here is that this is at what's called a redshift of 0.02. So that means that this galaxy and the supernova inside this galaxy is moving away from us at 2% the speed of light. Because the universe is expanding, which was discovered about 100 years ago now, the farther away we look in the universe, the faster everything is moving away from us. So we kind of use this as a proxy to tell how distant all of these various objects are. And so this one is, I think it's about 80 megaparsec, which is, I think it's like a factor of 3 for light years. So 120 million years for light to travel from that supernova to us, if I'm doing math correctly. So this is really, really, really far away, but it's actually one of the closer supernovae that we find and observe. So I just wanted to point that out. We can discover supernovae up to maybe 10 billion light years away.
David, can I put you on the spot for one more thing, and then I'll let you go because I know it's late for you. So if we're able to take the observations this evening, what might we expect to see? Do you have any other like previous observations with this instrument that you might be able to share with us?
Yeah, I didn't really prepare any, but let me just pull up a proposal really fast because we just had our most recent Gemini proposal deadline. So I put in a proposal for more of these same observations. And one of the things, have it here. So one of the things that we want to look at, this is just a tiny snapshot. So this is a couple of the spectra that Gemini has taken for us in the past. So it goes, it's leftmost end of the plot. These are 2 spectra. This is kind of just the very edge of the visible range, and then the rest is the near infrared. You can see some noise here, but also some interesting features. And one of these features,
David, sorry, I'll just point out that the dates there on the bottom right, maybe the format's a little bit odd, but this is March 21st, so near the vernal equinox, and March 30th of this year. So these were literally just taken week to 2 weeks ago. So basically, we took the observation. You got an alert that there was a supernova. We took the observations, and already you've used this in a proposal to take more observations, all within the course of 2 weeks. So this science moves very fast.
Yeah, I would say the amount of work that's required for me when I use Gemini is a factor about 10 less than if I were to use most other telescopes. I still have to look through various web pages of supernova discoveries and see what's interesting. But once that happens, then I can request the observations. It comes back to me. I run a data processing pipeline. This was Pipet in this case from Brian's wife. Thank you, Deborah.
I was gonna say, you must have a really good contact scientist to make that easy on you.
And yeah, and the data looks beautiful. So I'll show you, we haven't really done that much analysis of this data yet, but I kind of zoomed in on this one particular wavelength, and you can see from a plot from a different paper on the right, what this looks like in other supernovae. So first off, this is from supernova 2011 FE. That was the supernova that exploded in 2011. It was the second closest supernova that's been observed in the last like 15 years, something like that. And this was the earliest near infrared spectra they got at like minus 12.5 days before maximum light. So with this program, we think we found one even earlier than that, even though this one was just really close and easy to observe. So that just shows what's possible with all of these new surveys, finding supernovae all over the sky of order 20,000 per year right now. But then also when you look at the spectrum, this is a blend of a magnesium line and a carbon line. So what they're looking at is how this carbon feature is evolving as the supernova gets older, and you start to look at the inner layers of the supernova. For them, they had to do this kind of complex modeling where they summed up these 2 components and said, okay, this green line is what our carbon feature looks like. And that plus the magnesium 2 line, we think with some confidence that they're both there. For our first spectrum that we took in the blue, they're actually deblended. So you can just see both of these features separately, and they're pretty different in velocity space. So I don't really know what that means yet, or even if it's been seen before, but we're gonna go back to our theoretical models of how these supernovae explode and figure out exactly what the carbon might be doing in the outer layers of this explosion. So that's one of the things I'm excited about. I honestly did not know a whole lot about this particular part of supernova science before I started working on this proposal with a grad student at the UH Institute for Astronomy. But we're excited to do a bunch of modeling and figure it out. I should say type 1a supernovae are this object that we've studied very well for a lot of years at this point, but we're still confused on how they explode and what the system of stars that makes them explode is. It could be two white dwarfs that merge together eventually, or it could be a giant star near the end of its life that's pouring mass onto this white dwarf gradually until it hits some maximum mass and then it explodes. This is called the Chandrasekhar mass. And but we're not really sure how this happens. And so seeing the mix of elements in the layers of the explosion, that can tell you how nuclear fusion is happening in the detonation and what's actually triggering this detonation to begin with.
David, I wanted to add a couple of things to what you described, if that's okay. There were a few things that you could see on the screen that may not be obvious to the students. So, for example, it said MG Roman numeral 2, or it said capital C Roman numeral 1. This is a designation that spectroscopists use. Mg stands for magnesium in the periodic table, and the Roman numeral 2 means one electron has been removed from, by some physical process, an electron has been removed from that magnesium atom to create a magnesium ion, positively charged ion. Similarly, C1, so when you see 2, it means one electron has been removed. When you see C1, it means it's carbon, but it's a neutral atom of carbon without any ionization. And this may not be obvious. The other question that someone asked, I believe, is, supernova are important for a variety of reasons, not least of which is during the explosion of stars, either type 1As or other types of supernovae, but during the explosion, elements in the periodic table are produced. During, type 1As, you produce a lot of iron, the 26th element in the periodic table. And during, type 2 supernovae, where massive stars, the insides implode and the outsides explode, you produce a lot of the heavier elements in the periodic table. This is, so the understanding how elements in the periodic table formed requires understanding of supernovae. That's one of the reasons. There are other reasons why supernovae are important. They're very powerful. They can be seen out to large distances. Type 1As are standard candles in that all of them have the same intrinsic power. So there are many reasons why supernovae are important for studies, astronomical studies and cosmological studies. But one thing that comes to mind is understanding the periodic table requires understanding of supernovae. Anyway, I'll shut up here, but that was exciting to see.
It's easier to understand.
If I might add on, type 1a supernova specifically, that's the supernova where you have a white dwarf orbiting a red giant star, and the white dwarf is siphoning off material from the red giant star. Type 1a supernova, when they go off, they have a very consistent luminosity, which means that whenever we observe a supernova that it is a type 1a, we know exactly how bright it is. And that helps us with calculating very, very accurate distances. Since distances in astronomy is one of the hardest things to actually determine, because a light bulb that is very, very faint but close to you can look very similar to a light bulb that's very bright and far away. But if you know exactly what the wattage is of your light bulb, if you know exactly how much light that supernova is putting out, then you can calculate a very, very accurate distance to these different objects. And it took a long time for people to figure that out. And type 1 supernovae in galaxies is one of the best ways for us to get very, very accurate distances to galaxies.
That's very helpful. Thank you. Thank you.
Yeah, thanks a lot, Emily. I'm gonna let David go because he needs to sleep while we take his observations. So thank you very much, David, for joining us, and we will let you know in the morning how the observations turn out.
Awesome. Thank you guys so much. Have a good night.
Zach, Charlie, if you have a second, would you mind letting us know what's happening in the control room right now?
We're having a discussion about how accurate the type 1A luminosity value actually is. No, we are.
David just signed off. He can't defend himself.
Best of times then to discuss this.
That's the thing, though, is in science, we are constantly adjusting and seeing how things work together.
Revisiting our assumptions.
Exactly, revisiting assumptions. But really, distance is one of the, believe it or not, it's like one of the most basic things that you can, something that you can know about an object, but is also at the same time one of the hardest things to determine. Just because, like as I mentioned before, something that's faint and close looks very similar to something that's bright and far away. And knowing, there's a very, very simple equation that to calculate a distance, if you know exactly how bright an object is, but there's only so many objects that we do have it nailed down of how bright that object is. A great thing to research if you're interested in some of this is the cosmic distance ladder and how over hundreds and hundreds of years we've had to be really patient in order to build up how to calculate distances to objects.
As far as what's going on telescope-wise, we are in the middle of a Maroon X observation. Conditions still look pretty good.
This is still the exoplanet with radial velocity, right?
Maybe.
I mean, there are multiple programs that are exoplanets. So I can't remember what one we were on previously. So we may be back to another different target, but same program. But
Okay.
I can't. I can't
Is it still
recall.
exoplanets?
Yes.
Okay. Exoplanets are definitely like big leading science these days. Everybody wants to know more about what's going on with exoplanets.
And I wanted to inject a comment here, please, if it's okay.
Yes, go on.
Yes, please go ahead.
So you were talking about bright and faint, and I wanted to make a distinction here. There is intrinsic brightness and apparent brightness that I'd like to make a distinction between. There's how bright something appears to be to us, and versus how much power it is actually putting out. So intrinsic brightness is an intrinsic property of the object, tells you how much energy it is emitting per second. And apparent brightness depends on two things. It depends on the intrinsic brightness as well as its distance from us. So, but the advantage of apparent brightness is you can measure it. You could go off and measure it. You can measure how bright an object appears to be. And exactly as you said, if in addition to making that measurement, you know that it's a 100-watt light bulb, not a 200-watt light bulb or a 60-watt light bulb. If you know its wattage, if you know its intrinsic brightness through some other argument or through some other means, then you can determine distance.
Yep. And in astronomy, we also call that luminosity.
Got that luminosity, that's right. Absolute magnitude, intrinsic brightness, and luminosity are three different ways of expressing the same thing, which is the intrinsic energy output per second of an object.
Right.
Oh, somebody asked, we can find the exact distance by stellar parallax. That is true to a point. So parallax is where if you have things on two that are separated. So like if you stick out your finger and get up. So if I stick out my finger and I open one, I close one eye and open the other eye and I swap it, my finger jumps back and forth. And I could use how much that finger jumps, calculate the distance from my face to that finger. Now we can do stellar parallax by taking a look at a star during 2 different times of the year. So in June and December, and seeing how much the star shifts back and forth, calculate the distance to a star. And that's very, very good for stars. However, galaxies are very, very far away. And the amount that the galaxy is going to shift is going to be negligible with that parallax distance. So what I was talking about with the cosmic distance ladder is how we get to calculating distances is we find what works very well for things that are close to us. And then as we're approaching the point where that system is no longer working, we find the next best thing in order to look at something that's a little bit farther away. And then when we have that nailed down, we figure it out a little bit more. And that's why we call it a ladder, because you're stepping up the steps of the ladder. One of the earlier steps is that stellar parallax that we then use to calibrate the next step up for things that might be farther away. For galaxies, typically, the best things are Cepheid variable stars, which was discovered by Henrietta Leavitt, that Cepheid variable stars have a very consistent luminosity at a certain point. And then after Cepheid variable stars are type 1a supernova. I saw a lot coming in through the chat while I stood up, so I had...
Yeah, definitely.
Yeah.
Yeah, so parallax is pretty much good for a few tens of parsecs away, generally.
Gaia begs to differ.
Hmm?
Gaia begs.
How far does Gaia get out?
Kiloparsecs.
When are we getting out to kiloparsecs? Okay.
Somebody asked if the detection of a white hole through the James Webb Telescope is real or not. I have not heard of that discovery, and if we did discover a white hole, every single news outlet would be talking about
I'll go
it.
on and live and say no.
I don't think it is, because that would probably be the front page of every single newspaper if it was real. So sorry.
Which is a good lesson to the students to not believe everything they see in, in the media.
Exactly, yeah.
If you see it on the internet, it's probably not true.
Yep. But that's also, that also shows something in science of, that's another level of peer review. If only one news outlet is saying it and no other news outlet is corroborating it, that's peer review in action, to a fashion.
Not for a fashion.
The students may not be familiar with the term peer review.
So peer review in science is referring to something that you actually probably experience every day, where you say something and then you talk with other people who might have some level of expertise in that subject and then see if they agree or disagree. And then you all work together in order to figure out how much merit that claim actually has. So even like on the schoolyard sort of thing of, hey, I brought in a new Pokemon card and I really, really like it, but my friend says it's a fake. Then you go talk around to everybody who has some level of expertise in Pokemon cards to see if it's a fake or not, and that's a level of peer review. Now in science, it's a lot more intense. You get a lot more people who have a lot more specialized expertise on all of this, all talking and reviewing papers in order to go out. Even the people who are not scientists, the level of peer review can, like I mentioned before, is one news outlet says this, but what are other news outlets saying? What are other people who might be experts on that subject saying at the same time?
Well, and from a research perspective, that peer review ideally takes the form of a researcher who does their research. They publish their research for others to take a look at, and they publish their methods, their assumptions, their conclusions from all of that. And then other people who are experts in that field. So if I, as a high mass star formation researcher, I publish a paper that talks about high mass star formation, then as part of that publishing process, other researchers who study high mass star formation are going to look at that and say, yes, these methods are reasonable. These data appear to be reliable. And if all that's true, then these conclusions seem realistic. Or they might come back and say, you haven't thought about this case, and that would change your conclusion dramatically. And so it's a continual process by which we analyze our ideas, and frankly, we look for holes in the ideas. And I think that's one of the things that makes science kind of unique in what it does. We actively try to disprove the ideas that we have. If I have a really neat idea, one of the first thing and one of the biggest things I'm going to do is try to prove myself wrong, ideally. And if I keep going through that process of analyzing, of letting others take a look at my work, as we go through that process as a communal exercise, we can hone the idea, we can fine tune the idea, reject the bad parts and keep the good parts. And that's ideally how that scientific process works. It's what makes science different from just some other kind of storytelling, is we're actively trying to find the ways that we are wrong and eliminate those and adjust our idea until we have no more wrong things that we can find. So that's what that peer review process looks like as a scientific researcher.
Yeah.
In astronomy or really any other science.
Someone in the chat said, oh, so it's like an argument?
It's an argument, but it's not just a
It's a respectful
it's
argument, hopefully.
It depends. There's been some very not respectful. I've seen some very not respectful, but ideally it's a supported argument. It's not just, I think you're wrong. It's, I think you haven't considered these ideas, or I think your assumptions that you're making are sloppy, or you haven't, it's hopefully a very constructive argument, an argument in that very technical sense of a supported dialogue looking at the value of an idea.
Can we go to Q1 2013?
2013. All right, we are slewing. Our next target.
So sorry, can I just interrupt for a second? Zach, maybe could you just give us a quick overview of what just happened and why we're moving the telescope?
Yeah, so we finished our observation on the previous program, and now we're moving to another Maroon X program. So we are just like earlier, Charlie is moving the telescope to where we need to, where the target is, and then once guiding is established, then I will get the instrument set up.
We're
So I'm showing-
slewing to actually one of our more nearby stars.
Does that star have a name, Charlie?
It does. This is Wolf 359.
Oh,
Nice. Yeah.
Known to science fiction fans
I was gonna
everywhere.
say, if you.
I'm not sure if it's no star, but it's not anymore, but there's a.
Miss Battle.
It's about just a little under 8 light years away. So the light that we are collecting is about 8 years old.
So I'm sharing the TSD right now, the telescope status display. And for people, I think people can see it, yeah. And so for people online, Charlie is moving the telescope to a location that Zach requested. This is a program, a set of scientists that asked for observations with our Maroon X instrument. And
Zach, we are on target at 200 hertz.
And so the background chatter there is Charlie, who's the operator tonight, letting Zach know that we are in position now. This is why things on this telescope status display have turned green. And we're guiding on a guide star, which means we have very precise pointing and tracking with the telescope. And so I think Zach now, actually, maybe I'll go to a different screen. 1 second. So Zach now is going to get a very high precision centering of this star. So Charlie's done the course alignment, and the fiber, the science fiber that collects the light is this red and blue circle that's flashing right now. The star that we're targeting is just to the bottom left of that. Zach is using this nifty MaroonX software to grab the star, and there's an internal tilt mirror within the MaroonX instrument that's changing a little bit. So you can see this TT axis 1, TT axis 2. It moves on two axes, and it allows the light to be piped to the science fiber. So everything's green now. Before it was red. Everything's green now, which means we're on target. And you can see on the right-hand side a graph that gives the number of counts. So basically the number of photons that are being detected per second, or per millisecond, I guess, in this case. And you can see right here on the, oh, Zach just reset it. So Zach, being the conscientious observer, just reset the plot so that now we can make sure that the counts are stable throughout the course of the observation. So MaroonX is reading on the science fiber many times per second the number of counts. And if we see a drop at those counts, that may indicate a change in the atmosphere. That may change, maybe a change in the amount of blurring of the atmosphere. Clouds could come in. Something could happen with our instrument, with our telescope, heaven forbid. And so we want to monitor that the whole entire time of the observation to make sure that we're getting the quality of observation that is requested by the proposing scientists. So it looks like he feels that we have stable enough counts, that we're centered well enough, and he's just started the exposure. So this looks like it's going to be a half-an-hour exposure. This will probably close out the session, I guess. And so now the job of Charlie and Zach is just to let the telescope do its work, to collect the light and make sure that we don't have any drift away from the source that we're intending to target, and that the conditions don't change dramatically such that we need to move to a different target to get the conditions that match the requests by the scientists that propose.
Stop
And
it.
so
Stop it. Don't change this. Stop it.
Sorry.
Thanks, that's Brian. Don't talk about
Okay,
don't
got it.
talk
Sorry,
about
sorry.
lousy weather or weather changes here.
Oh, come on, Charlie. This is the best weather we've had on the Shadow of the Scientist session.
Right. Just stop talking about it. What everybody should know is that
so we have wonderful
scientists, we are
conditions. I'm
not
sure they'll
superstitious
continue
at
ad
all. But
infinitum with
telescope
Charlie at the helm.
operators, we are very superstitious. There are
Yeah,
some
so
things
despite
you
all the
don't
peer
talk
review
about.
and all these reasoned arguments, it turns out at nighttime all that goes away, and we try to.
All that goes away.
No, but we try to use critical thinking, and then when when we're at the mercy of the elements, then we just resort to superstition, like I think most people do.
Atmospheric science is hard, and yeah, superstition will start to take over. Do not talk about how good the weather is. You can talk about how bad it is. You can't talk about how good it is.
So speaking of the peer review process, so Zach just asked Charlie to move to a certain observation. This is he mentioned a program ID, and this is we have a pool of observations called a queue, and these set of observations are proposed for. Again, as I mentioned in the beginning of the session, a group of scientists then determine which ideas that people propose for have the most scientific merit. and then time is awarded on the telescope in various tiers based on how good the science ideas are deemed to be. And then when we create a plan for a given night, we choose the best science, the most highly ranked science for the conditions. And so again, the conditions I won't mention, but we're doing pretty well this evening. And so this observation was planned in our better weather variants. So if the conditions were reasonably good, we could go to this observation. Perhaps if the conditions were worse, we'd have to move to a different observation.
You guys, a lot of people who are just joining, or people are continuously joining, I guess, don't have a good sense that, for example, that we're effectively using two different instruments at the same time. You're using a guider camera to take images of the sky, while you're also using a spectrograph to take one of the objects on that guider camera image and split up its light into the colors of the rainbow.
Yep, that's exactly right, Raja. So actually, I just brought up another screen here. So I'm mirroring Zach's screens, his observing screens, and I brought up one of his 8 screens. So this is screen number 6. And what you can see on this picture is I'm non-interactive, so I can't zoom in, but on the left-hand side, so in this display right here, you can see a couple of crosshairs. This is our guider. Sorry, this is peripheral wavefront sensor 2, probably. So this is one of our wavefront sensors. So basically a way to find a guide star and to track on that guide star. And so this is probably, no, sorry, is this a scientific target, Charlie?
Yes.
Yeah. Okay, so that's the cast rotator center. So this is basically the science target, and then I guess
Sorry, that middle window is a guide star.
the middle window. Okay, all right.
That middle window is the guide star.
So this is P2.
That is the acquisition camera.
Okay.
So we actually, the guiding process, we use a couple of different cameras. We use a much wider field camera called the acquisition camera to help us line up on the guide star. And then once we've got that star into those, into the middle of those crosshairs, then we switch to the actual guidance camera. If you switch to, well, I guess you're not if you have the ability to switch over to LD2 monitor 5, you can see the actual guide star guidance camera P2 on my monitor here.
So that's on the bottom.
If you take a look at down at the lower left here, let me move that for you. This is what the window over here at that far lower left corner is what the guider looks like. It consists of a 2x2 lenslet, so it looks like a box that's really just 4 lenses making 4 images of the same star. That's not a box in space. And that 2x2 array enables the guidance camera not just to point the telescope in the right place, but it also allows the telescope mirrors to deform a little bit to have the right shape to keep the image in focus, to remove astigmatism, which is an optical aberration, to smear the image out, tends to smear point sources like a star into an arc. But that's why it shows that little box array. So for my monitor here, we've got the acquisition camera in the middle We center up on that first, and then once we're there, we switch over to the guidance camera in the lower left, and then we can close the loops and actually just start guiding on that.
So maybe I can see if I can bring up an OT here.
Yeah.
Yes, everything.
So I know earlier on in the chat, we had a lot of questions about black holes. And so I can like briefly describe a black hole real quick. Oh, somebody
Yeah,
actually
please,
just, okay. Somebody put a good explanation in the chat as well, but essentially the best way to think about black holes is you start with the fabric of the universe. And the best way to conceptualize this, we're going to take all the dimensions of the universe, and in our model, we're just going to collapse them all down to 2 dimensions and just imagine a bed sheet that you're stretched out, like getting ready to make your bed, and it's stretched out nice and taut. And that bed sheet represents a 2D model of the fabric of the universe. And then you take a bowling ball or anything that's heavy, and you drop it in that bed sheet. And that bowling ball represents anything in the universe that has mass. And that mass is going to cause that bed sheet, which is space-time, to then warp down. And that's gravity. Now, everything that has gravity in that bed sheet is creating that gravitational well. And if you're standing on the surface of that bowling ball, depending on how much gravity is getting, like how deep that gravitational well the bowling ball is creating, if you're standing on the surface of that bowling ball, if you were to jump up off of the bowling ball at a certain speed, you would be able to get up out of the gravitational well and be away from the influence of the gravity of the object. And that's the escape velocity. So every object in the universe that has mass creates a gravitational well. And then we also have associated with that gravity well escape velocity. If you're on the surface of that object, the speed that you would be able to jump up in order to get away. What a black hole is, theoretically, is if you take that bowling ball, you take that object, make that gravity well, you make it the most heavy, massive, dense thing that you could possibly imagine. It's so massive and it's so dense, it's pulling that gravitational well down so far that if you were standing on the surface of the object at a point, what we call the event horizon, in order to jump up and away from the surface, you would have to travel faster than the speed of light. The escape velocity for the object would be faster than the speed of light. And as many of us probably all know, the speed of that is impossible to do. You guys are all young, wonderful students. You guys are going to be able to do so many amazing things in your lifetimes. The number one thing you're not going to be able to do in your life is travel faster than the speed of light. And that's our black hole. That is our singularity. And that is the definition of the black hole. It's something that is so massive, so dense, that if you're standing on the surface, there's no way that you can jump up and get away with it. How is it created? Most black holes that we know of are created via supernova. And not quite the supernova that we were observing earlier on in the night. Earlier on in the night, we were observing type 1a supernova. That's when you have a white dwarf siphoning off material from a red giant star, and eventually it explodes. A type 2 supernova, which is just the most biggest massive stars that you can imagine in the universe, exploding. During that core collapse, when that star comes to the end of its lifetime, its core collapses in on itself, and that creates a lot of mass into one very, very dense object, and that is when our singularity can form. That is when our black hole can form. Yes, the death of stars. I have so many people coming in the chat at once, it's hard for me to keep up with you guys, but I do see some amazing ideas.
Emily, if I can correct just one thing.
Yeah, go on.
That is how stellar mass black holes are formed, which is actually by far the smaller number of black holes that we're aware of.
But do we know how the big ones form?
The big ones, we've got some ideas of how the big ones form, but we do not think they form anywhere near the same way. They seem to be, I think the leading theories are more of a direct mass collapse. They had nothing to do with the star, but rather formed very early on and then just kept growing as they absorbed more mass. We should note that, the idea of a black hole as sort of something that's just going to suck everything up is really not an accurate idea. It works well in science fiction, but that's not what they're really like. They're just like anything else with mass.
Exactly. And if we go back to our bowling ball in the spreadsheet, by definition, what really a black hole is an object that if you're standing on the surface of the object, no matter how fast you jumped up in the air, you would never ever be able to escape it. But have any of you guys jumped up in the air and escaped the gravity of the Earth? In order to do that, you'd have to jump up and reach the height of 3 Maunakeas in 1 second. I try it so many times and I never get there. But the Earth still has
Kilometers per second.
Yeah. The Earth still has a moon orbiting around us. The moon don't care about escape velocity. You don't need to care about escape velocity if you're not touching the surface of an object. So just in the way that we can't escape from the Earth's gravity by just jumping up in the air, but the moon still orbits around us, if an object can orbit around a black hole. And that's actually how we discovered the black hole in the center of our own Milky Way galaxy. We watched as stars were orbiting around the black hole in the center of our galaxy. Now, many people are talking about white holes. White holes are purely theoretical. And I'm honestly, they're so theoretical, I have a difficult time describing them completely accurately. It's essentially the opposite of a black hole, where instead of material falling in, material will be getting ejected out. Now, there are 2 camps in astronomy. There's the theorists and there's the observers. The theorists are the people who really, really love math and will work for day in and day out thinking about math and equations and using those math and equations in order to make predictions about the universe. And then those theorists will pass the predictions on to us here at Gemini Observatory, where we are the observers. And we're going to take those predictions, we'll use our observatories to then see if we can find evidence that supports or refutes what the observers are coming up with. And the system works for most things. However, there are some things in the universe that you can theorize, you can make a prediction, but due to the nature of the universe, we're never going to be able to find out whether or not it's right. Big question, what happens when you fall into a black hole? Theorists love to come up with theories about that, but because we cannot observe past the event horizon of a black hole, us observers here at Gemini Observatory, we're never going to really be able to confirm or refute that. Now getting into white holes, wormholes. A white hole, best way to create a wormhole would be to connect a black hole to a white hole, and then you could potentially travel through it. The issue is we do not observe any white holes in our universe. That means that there could be a white hole in the universe that's next door, but we don't know that they're there. So if you did fall into a black hole and it was connected to a white hole in the nearby universe, there's also no way for you to get back because we don't have any white holes in our universe. There's so many questions coming in, I can't quite get all.
We should note that a white hole is really just a mathematical, it's a name for one aspect of the mathematics that comes out. Mm-hmm. It's not anything that we even, we don't even look for it because the characteristics that it have are things that we've never ever seen. So it's a mathematical structure, basically. It's an idea, but it is not a reality that we have ever been, as Emily said, that we've ever been able to.
It's something that the theorists really, really love, but we have no evidence that they exist in
the theorists really, really love that. I think it's something that science fiction authors really, really love. But I don't think that's. I've never met a theorist that thought to cents for that.
I love it enough that I hear the question about white holes all the time from students. Yeah. And now I do see people spam in the chat about, can we time travel? You are currently time traveling.
Emily, I removed that person since they spammed the chat. So I just want to remind people that being respectful in the chat is really important. So that
thank you.
gets a chance to ask questions, and we're not going to be able to answer all the questions this evening. But there are plenty of other Shadow of the Scientist sessions, both on Gemini North and other telescopes, where we can discuss ourselves or other scientists can discuss the answers to these questions. So why don't we forego that question? Maybe we can answer some of the other questions that are in the chat. I just wanted to point out, going back to the conversation that we had earlier about guiding, and maybe go to a little bit less theoretical concept, since we are on sky and we are observationalists. That this is actually this picture that I'm sharing right now is not the observation that we're taking, but it's an observation similar to the observation that we're taking right now, where we have a bright star in the middle. So this is our observing tool. This is a picture of a particular part of the sky that has a bright star that we use for a calibrator. Our instrument is pointed, so in this case, Zach is pointing the Maroon X instrument at a star like this star. And we have this peripheral wavefront sensor 2, which is outlined in this in yellow here, which is acting as our, so is pointing at a guide star. So we have a bright star as a target, and that's what we're looking at with Maroon X. And we have a less bright star that we're using as a fine guidance. We're using our guiding sensor to make sure that the telescope tracks correctly and keeps our science target completely in our science fibers, so that we get the maximal amount of light that we can possibly get into our instrument. And so just to give people an idea, the precision with which we need to center the science target is roughly 1 arc second. So I think the Maroon X fiber, Charlie, Zach, correct me if I'm wrong, is roughly 0.74 arc seconds.
That sounds right.
And so an arc second is if you hold your arm, if you hold a finger at arm's length, you hold that up to the sky, and the angular space that is covered by your fingernail, that is roughly 1 degree. 1 arc second is 1/3600th of that. So roughly 1/3600th of a fingernail. That's what we have to point our telescope at. And we have to keep the telescope pointed for a half an hour at the exact right location, with the Earth rotating about its own axis, with the Earth rotating around the sun, and various components of the Milky Way, including the guide star, moving with respect to each other. So we have to do all of that with these incredible sensors, and this is what allows us to do that.
Brian, it's worth noting that your example there is using a standard, which is a particularly bright star. And in most cases, the guide star is brighter than the science target. So it's swapped, where we're looking at something bright with the guider and something faint on science.
Yeah, so I think in this particular case, the Maroon X observation, probably we're looking at something fairly bright, maybe not this bright, but reasonably bright. It's because the spectrograph is so high resolution that it's dispersing all of the light out very finely. And so we need a very, very bright object in order to get enough light to be able to handle that level of resolution. If we had a lower resolution instrument, we could look much, much fainter. So in this example, I think we're using GNIRS, which is the instrument that David was speaking about earlier, and then we'll take the observations with the supernova later this evening. And that's a much lower resolution instrument. And lower doesn't necessarily mean worse. It just means that certain science cases don't need to resolve light spectrally as much. And so in this particular case, we're able to look at something much, much fainter because we don't disperse the light as finely as we do with the Maroon X instrument. And I think we're getting close to time, so maybe we could pick a couple other questions in the chat, Emily, and
Sure.
answer them, and then we could Jamika maybe could close us out with a few words, and Raja as well.
Yeah, so I think I'll just kind of expand a bit on what we were talking about with black holes and gravity, since I saw some people in the chat kind of mention this, like how do we detect black holes if they're not emitting light? First option is to observe things that the black hole is interacting with. For example, at the center of our Milky Way galaxy, we have a supermassive black hole that has a lot of stars, a whole family of stars orbiting around it. And that is the main way that we detected the black hole in our center of our galaxy. We watched these stars, we watched how fast they were moving and calculated, well, what needs to be making that gravitational well in order for those stars to be moving in the way that they were. And our conclusion was a supermassive black hole. You can also use other types of telescopes. So we're an optical telescope here at Gemini Observatory. You can use some millimeter and radio telescopes to create an image of a black hole. If you're interested in researching that, look up the Event Horizon Telescope. It's a really, really excellent project. It took the first ever picture of a black hole back in 2019, and that black hole is named Povehi, which is a Hawaiian name. So it was picture was partially taken here and then given a Hawaiian name to honor the culture of Hawaii. That's a really, really excellent research to look into. But
Emily,
talking
can I just
about
interject for a second? Because there's a kind of fun thing happening. So just downstairs from us, just to show how close-knit the Maunakea community is, we have one of our Gemini North staff members. So he supports Gemini North, an optical near-infrared telescope. And he's actually observing on the Event Horizon Telescope right now. So there was a trigger for the past 3 days, and he's part of the Event Horizon team. And so literally like the floor down from us. So Mark Rawlings is observing with the Event Horizon Telescope right now as we're observing on Gemini North.
Oh, that's exciting. More pictures of black holes. But then the last thing to mention, here, I'll leave you guys with like a mind-blowing thing. So the other way that we are now getting in order to detect things in the universe is via gravitational waves. And that goes back, if you imagine that bed sheet that is our space-time, you have that bowling ball in the bed sheet. And if that bowling ball moves, it's going to create a ripple across space-time, and that's a gravitational wave. Those were first theorized by Einstein, but were not observed until just about 5 years ago. It was the first time we ever observed gravitational waves.
Longer than that by now, but yeah.
Yeah. But oh yeah, look at that. But it's 2024 now. Anyway.
What, 9-10 years ago? Maybe?
Yeah, it was 2015. Oh man. Okay, anyway, that's not the point. But gravitational waves are a new way for us to be studying things in the universe. A gravitational wave is created when an object with mass moves in the universe. And the gravitational waves that we can detect are from the objects that are the biggest, the most massive objects moving very, very quickly. So right now we detect gravitational waves from black holes colliding, from neutron stars colliding. But anything that has mass and moves can create a gravitational wave. And as we calibrate our instruments, we might get to a point where we're detecting gravitational waves of different types of objects. The reason why this is so exciting is all of astronomy up to this point in history has been done with light. Everything that we currently understand about the universe, we understand because of light. And at its most basic, light is created. Light is the electromagnetic spectrum. It's when an electron drops from one valence level to another in the atom that emits light. And that is the basis of how we've been able to understand everything in the universe. And we understand a lot from light. But now we are able to detect gravitational waves, and we're now able to study light, to study the universe using something that is a completely different tool and is not related to light at all. And that is what LIGO is doing. LIGO is a gravitational wave detector that they'll detect things in the universe. The signal will go out to observatories like us here at Gemini, and we'll stop what we're doing and we'll go look at that object and compare our observations with light and with gravitational waves. And we're And we're unlocking secrets about the universe of things that we might not have ever been able to see before going off of light. To me, the most mind-blowing thing about gravitational waves that we're still completely understanding is that gravitational waves travel at the speed of light, which is mind-blowing because the two mechanisms of how these things, how the ways that we can study the universe, they're not connected at all. So that indicates to us that there's still so much more that we can understand about the nature of the universe, the physics of the universe that we all live in.
One of the things I can add, since you're mentioning LIGO, we have 2 LIGO observatories in the United States. There's one in Italy, and there is one that is planned for construction in India. I am not sure what the state of that is, but we are building more gravitational wave observatories, as Emily mentioned. It's a very exciting new area for study that can tell us some things that light has not been able to tell us. So yeah, there's one that's been planned in the planning process. I'm not sure what the status of that is in India.
Okay.
So I was going to wrap
Thank
it
you.
up, but I was going to say citizen science projects, check out Zooniverse. That's the best place for citizen science projects for students.
I'm
In my
typing
opinion.
it into the chat.
Okay, thank you.
Thank you, everyone, for joining us. I'm in the process of sending out an email to everyone who's registered to invite them to Raja's upcoming sessions, which will be the next 2 days at this same time. So thank you again, and we're wishing everyone a wonderful day. Aloha.
Bye, everyone.
Mahalo nui loa for everyone joining us.
Yeah, and thank you, Ekta, for your heroic efforts in the chat there, and Zach and Charlie for allowing us to shadow you, and Jamika
Amazing.
for making all this happen.
Thank you all.
Yay, Jamaica.
Thank you, everybody. Good night. Good day.
Bye.